course, which is dynamic programming. Ali might have started parts of it already in his recitations. Two announcements before I begin. The first one is about the exams that you turned in for regrading. They've been regraded. The grade should be up on Courseworks. The answer books are with Ali. If he comes in today, he'll bring it in this class, or you'll definitely get it in the afternoon. The second one is that some people who were scheduled to take their exam in the Davis auditorium complained that the auditorium is not the best place to take an exam. So we have gotten an alternative room. It's halfway across the campus in 702 Hamilton. I'm totally indifferent between the auditorium or 702 Hamilton. If the students prefer 702 Hamilton, then we'll have it there. And that's a regular classroom. So does anybody have any strong objections to moving to 702 Hamilton?
Isn't Davis better?
What?
Isn't Davis better than Hamilton?
There are people who complain that Davis is worse.
I don't think they know what Hamilton is.
Okay. So, all right. So why don't you go on an expedition to go check out Hamilton?
I don't think Hamilton's better.
Unfortunately, all the other classrooms are being taken over by ACES for doing their upgrade. All right, so it doesn't have to be resolved right now because both rooms are reserved for the period, and we can go either way. Okay, so the last story for this course is dynamic programming, and instead of giving you a formal definition, I just want to give you a bunch of examples. And we'll start off with this capital budgeting example and try to give a logic for why dynamic programming is useful. Could we settle down, please? If you have a question, ask me. Thank you. A little bit more. I noticed some of you were printing 4 pages to a page of the lecture notes. So I've uploaded this other version which has everything compressed into 4 pages of the physical notes are onto 1 page, if you would rather print that. Okay, so here's the problem. The problem is that you've got 5 million to spend. It always seems good to have large numbers. And what you want to do is use this money to upgrade 3 different plants. So this should be plant 3, not plant 1. So there's you're running 3 different plants, plant 1, plant 2, and plant 3. You've got a total of $5 million to spend, and each of these plants have submitted 1 or more upgrade plans. So plant 2 has submitted 3 different upgrade plans. This is the cost of plant 2, and this is the expected reward from that plan. So it costs $2 million, and you expect to reap $8 million from it. Plant 1 has only submitted 2 proposals, and plant 3 has submitted only 1. Zeros basically means do nothing. You don't invest anything in that plant, you don't get anything from the investment. And you have a constraint that at most 1 proposal should be accepted from each of these plants. And what you want to do is, of course, spend your 5 million judiciously so that you can maximize the reward that you can get. Here is the integer programming formulation for this problem. x1k, so here the variable x1k would stand for accept proposal k from plant 1, or let's say plant j. So xjk, the 2 variables, this is the interpretation of that. So if xjk is equal to 1, it means that from plant j you're accepting proposal k. This is simply the budget constraint. It says that I'm just taking the cost parameters. The first project from plant 1 costs, should have been a 1 here. So 1x11 plus 2x12. This is simply 2x21, 3x22 plus 4x23 plus x31 is less than or equal to 5, the total budget that you have. These 2 constraints here are saying that you can at most select 1 proposal from each plant. The last one has only 1 proposal available, and since I allow xij to be 0 or 1, I don't need to put a constraint for that one. So that's the integer program, and it's maximizing the total reward that you get from accepting the projects. And this is where we would have stopped if we were using only the techniques that we have learned so far. Now what we want to do is see if this particular problem can be solved in some efficient manner. The brute force technique for solving this is to look at all possible combinations, and how many combinations are there? There is 3 times 4 times 2, 24 combinations in this case. Many of them are infeasible because they violate this budget constraint. But in a total enumeration case, you will have to enumerate that, check whether it violates the budget constraints, and then get rid of it. Many of them are clearly dominated by others, and therefore, for example, the proposal 000 is clearly dominated, and that should not be considered. And so there must be some more efficient way of dealing with this problem. And one way of dealing with it is to recognize that the only thing connecting the decisions on these 3 plans is this budget constraint. If this constraint were absent, somehow you were able to get rid of this constraint, then the 3 decisions are independent. Suppose I told you a priori how much money you want to spend on plan 1, plan 2, and plan 3. Instead of giving you a total budget, I told you exactly how I'm going to split up this money. Then the problem is trivial, because you just have to select the most profitable one in each particular plant and decide what you want to do. So dynamic programming essentially tries to do the same thing. It tries to get rid of this linking constraint, this constraint that linked the decisions between companies, delink it somehow by defining states, so that if you define a state, then you can treat the 3 plants separately. Let's just go through the mechanics and it'll become clearer what I'm talking about. So we're going to pretend as if we're going to solve this problem in 3 stages. This is completely artificial. This construction of trying to solve this problem in 3 stages is my construction. It's not that the problem should be solved in that way. It's simply that if you want to think about it in dynamic programming, this is how we're going to do. And in stage I, so I takes values 1, 2, and 3, I'm going to decide the optimum allocation for all plants j less than equal to I. So in stage 1, I'm going to talk about plant 1. In stage 2, I'm going to talk about plant 1 and 2. And in stage 3, I'm going to talk about plant 1, 2, and 3. And each stage, I'm going to solve the problem for several different states. And what is a state here? State is the minimal information required to solve that problem. So if I'm trying to, so let's look at stage 2. So in stage 2, I'm going to look for the optimum allocation for plants 1 and 2. I'm not going to bother about 3 for the moment. I'm only concerned in plants j less than equal to I. I in this case is 2, so I'm looking for plants 1 and 2. And now what I want to do is I want to solve this problem for different values of the state. What is the state in this case? What is the information I need to solve this problem? The information or the quantity that needs to be supplied to me is basically the budget available. Remember, in the original problem, the integer program or the decision problem, whatever you want to talk about, the total budget, 5 million, is to be distributed over 3 plants. Here, we are not concerned about the 3 plants. We are only talking about plants 1 and 2. So, a priori, we do not know how much money will be available to allocate to plants 1 and 2. It could be 0, it could be 1, it could be 2, it could be 3. So I'm going to solve this problem for budget equal to 0, 1, 2, 3, 4, and 5. Why do I stop at 5? Because that's the total budget available for all 3 plants. So the maximum budget that can be available for plants 1 and 2 can be at most 5. All right? So this is sort of a crucial part in dynamic programming. Remember this, and when we criticize dynamic programming after I've shown you a bunch of examples, this story will come in. Have to solve the problem for a number of states. And this is a big problem. Initially, I've been given a problem. The initial problem, the problem that I'm trying to solve is this integer program. It's very well defined. I just want the solution for that problem. In the process of trying to get there, here I'm sitting in stage 2, and I'm claiming that I need to solve this problem for all of these different states. So if the number of states is large, meaning that the total budget, let's say, instead of having been 5, is 100, I'm going to have to solve 100 problems here in order to go forward. So keep this in mind, and this is a criticism against dynamic programming. Okay. The other thing that the state must do, and this would not become very clear in the first example, but I'll try to motivate it, and as we go along the examples it become clearer and clearer, I'm hoping, is that the state decouples the stages. And what it basically does is that, suppose I'm sitting in stage 2 and somebody told me you have $3 million to spend. I don't really care of how the remaining $2 million were spent for the other company. I don't really care. In terms of trying to solve the optimum solution for this particular problem, all I care about what is available to me now. What I do with this is not going to change anything for plant 3. It may be that putting $3 million for plant 1 and 2 is not optimum. That may very well be the case, but suppose I make that decision, then what I do in plant 3 is completely independent of what happens in plant 1 and 2. So that's what I mean by saying it decouples. Given the state, the problem splits up. There's a problem for plants 1 and 2, and there's a problem for plant 3. And we want to use this decoupling to be able to solve it more efficiently. For now, let's just say that we keep these ideas in mind. I'm not saying that this should become clear immediately, but this is sort of what the idea of a state is. It's supposed to break the problem down into pieces so that I don't have to solve a large problem, and I'm going to solve a smaller problem. But the cost that I pay for solving a smaller problem is that I have to solve many of them. So that's what dynamic programming is trying to do. It's going to try to decouple the problem so that it becomes a less complex problem, but it'll have to solve many of them. So let's start off. So what happens in stage 1? So in stage 1, all I'm trying to figure out is that if I have S dollars available, so S is the state, and the state takes values again 0, 1, 2, 3, 4, and 5, I want to figure out if S dollars are available to me to spend on plant 1, what is the best thing I can do? That's basically the story. So if you have $0 available, then the optimum thing to do is nothing, which is the first proposal that the plant gave. And what is the best revenue that you get out of that? 0. So V1 of S would stand for the maximum revenue that can be generated by looking at plants 1 if you have S million dollars available to you. So if you have 0, the best you can do is 0. If you have $1 million available, then you go back to the cost matrix over there. Let's see if I can keep, let me put this cost matrix down here so that we'll be using it over and over again. So the cost matrix is plant 1, plant 2, and plant 3. So the first proposal is 0, 0, 0, 0, 0, 0. The second proposal is 1 and 5, 2 and 6. This guy has proposals 2, 3, and 4 with gains 8, 9, and 12. And this guy has a cost of 1 and 4. So this is the cost matrix. And we have arbitrarily labeled these different proposals at 1, 2, 3, and 4. So going back to that derivation there for state 1, so we don't care about these two plants anymore. They are not there in the picture at all. And yes?
Why are we so constrained such that we only have to take a budget from 0, 1, 2, 5, 2, 4, 3, 4, 5, such integer values?
You tell me the answer. Why are we so concerned? Why are we constrained? Why would 4.5 be useless to consider here? So the question is, why do I consider states to be just 0, 1, 2, 3, 4, and 5? Would 4.5 be an interesting number to look at in this particular case? What?
Expenses are integers.
Expenses are integers. All the costs for the various projects are integers. I will never get the total budget that I'll be spending on a given plant will always take integer values. On the other hand, if this cost was 2.25, then what would happen? Then what kind of stage do I have to consider?
You will have to consider a quarter of a million.
You will have, basically what you have to do if you really want to conserve on states, what you want to figure out is what is the lattice generated by the costs, but a simpler solution would be to like 0, a quarter, a half, 3/4, 1, and so on. So it all depends on what are these costs. If the costs are integers, I know everything in this whole problem will be integers. If the cost is whatever it is, I have to accordingly look at it. Okay? All right. So given that, now let's just see if this table makes sense. So if I have $3 million to spend on this company, on this particular plant, what would I do? Since I'm constrained to use only one project, I cannot take two projects. If I have $3 million, the best thing for me to do is to spend $2 million and select project 3 and get $6 million as the best revenue. And that's what this particular line here tells me. If I have $3 million available, the K1 star, the project that I'm going to choose is going to be 3, and the revenue that I'm going to get from that is 6. All right? So is this table clear to everybody? This is sort of the starting point of dynamic programming. This is the simplest problem. This is as if we started with the integer program where plant 2 and 3 were not there. If plant 2 and 3 were not there, writing out this table is a pretty simple exercise. Just find the best thing that you can afford and write out the revenue of that. Now the next step is where the power of dynamic programming comes. This step, all we have done is total enumeration. We have just looked at what is the total money that I could spend from 0 to 5, and for each particular choice I've listed out what the solution is. It's just enumeration, nothing more than that. Now what we want to do is look at stage 2. And what are we doing in stage 2? In stage 2, what we are saying is that we are going to look at the best revenue that I can generate using plants 1 and plant 2. If I select project K from plant 1 and project L from plant 2, then the total cost would be C1K plus C2L. That should be less than equal to the state, which is S. The total budget that is available for the two plants, I must have that C1K plus C2L must be less than equal to S. And what is the revenue that I get from there? R1K and R2L. So those are the revenue that I get from there, and I want to maximize the revenue subject to the budget constraint. So the top line here is simply restatement of the integer program. It's using different symbols, but it's exactly the same. The second line here is the crucial thing that happens in dynamic programming. This is the recursion. Here what we are saying is the following. If we understand this step, dynamic programming will become much simpler. So what we are saying here is I write out what is the expression for V2S. This is simply saying that you want to maximize the revenue by choosing some project from plant 1, some project from plant 2, such that the cost of those projects is less than equal to S. This is simply the definition of what V2S stands for. The maximum revenue that you can generate using S dollars from plants 1 and 2. Now what we are saying is that suppose I decide to choose, so the second expression there is the following. So suppose I choose project L from plant 2. I don't know whether this is optimum or not, but suppose I choose project L from plant 2. How much money could I spend on this project? What is the maximum amount of money that I could spend on this project? S. So I must have the constraint that C2L must be less than equal to S. Now, if I decide to choose a particular project with cost C2L, how much money do I have left for plant 1? S minus C2L. So the budget for plant 1 is going to be S minus C2L. And what is the best revenue that I could generate using this money? Well, numbers don't make sense here, right? So if that is the budget that's available, then the maximum revenue is going to be V1 of this state, S minus C2L. Maximum revenue from plant 1. And that's crucial. This is just the revenue from plant 1. We haven't looked at the total revenue yet. Is this step clear to everyone? Because this is sort of the crucial part of dynamic programming. Once you realize that what you can do is write the solution for stage 2 by looking at the solution for stage 1. You get a recursion, and this has a name because this gentleman named Bellman first figured out that you could do it this way. So what we are doing is, this is the problem that we want to solve, but now we recognize that if I choose something for plant 2, I know how much budget is available for plant 1. This is the state for stage 1. Once I know the state for stage 1, I know what the best I can do, because I've already solved it for all possible states in that particular stage. And therefore, this expression can now be written as an alternative expression. Take the maximum of the revenue that you can get from the project in stage 2, meaning plant 2, plus look at the best you can do from the remaining money invested into plant 1, and take the maximum over all projects that are affordable. Is that step clear to everyone, how that restatement happened? Okay, now let's just try it out for a particular value of S, and then we'll fill up the table. So suppose we want to compute V2 of 4. So I have $4 million available, and I can distribute that $4 million any which way I want between plant 2 and plant 1. So what are the things I can do? Suppose I decide to spend $0 on plant 2. What do I get? So I get nothing from plant 2 plus V1 of 4. Suppose I decide to spend 1 on plant 2. What do I get? Let me just see if I've written down this cost correctly. Just want to make sure that I haven't goofed up. Okay, no, it's fine. So if I decide to spend $1 million, what is the revenue? Is there a project that's available here which would allow me to choose $1 million? No. No. So here, spending $1 million on plant 2 does not make any sense. The next cheapest project is at $2 million, so $1 million is not going to get me anything. So it's going to be the revenue from the next project, which is 8 plus V1 of what is remaining now? 2. If I spend 3 here, then I get 9 plus V1 of 3. And finally 12 plus V1 of 0. What happened? Oh yeah, this one. V1 of 1. Yes. Sorry. All right. And if you do that, what do you end up getting? What is the best thing? Here is the calculation. First one, you get V1 of 4 is equal to 3. I'm hoping this calculation is correct. If not, V1 of 4 is what? So that's a typo that I'll fix. V1 of 4 is 6. What about the next one? It's 8 plus what is V1 of 2? Just look at the previous table over there. 6, 9, and what is V1 of 1? 5. And what is V1 of 0? That's 0 and 12. So the maximum turns out to be 14, and the best project, K2 star, is going to be 2 or 3. It doesn't really matter. You can choose either project 2 or project 3 and they'll give you the same benefits. And this table basically does the same calculation for different values of the budget S. So this is the calculation we just did up here. V2 of 4 is 14 and the optimum is 2 or 3. Right? So already you should start thinking to yourself that dynamic programming may not be always the best thing to do in a problem. It's a simple calculation. The recursions are typically very simple. All dynamic programming recursions are of this nature. Decide what you want to do in this stage, and then the answer for the previous stage is already known. You've already computed that. So it's just a matter of adding a few things and taking a maximum. But this particular function has to be computed for all values of the state. You could be a little bit more intelligent and say, well, certain values of states are completely unimportant. For example, you needn't compare 0 in some sense. But you have to enumerate all possible states. And as we had discussed just a little while ago, if, say, the budgets were in quarters, then the number of states is going to be huge. And that has to be done in every stage. You have to compute this value for every state in every stage. So you have to judiciously think whether it's worth it for you or not. Okay, once we've done that, now we go to the next stage. So the next stage, we just want to compute V3 of 5. So this is the answer we are looking for. What is the best revenue that I could get from using the 3 plants and $5 million? So this is the only value that I need, V3 of 5. So all of the calculations that were done up to this point were simply to compute this number. In order to compute this number, I had to compute V1 of S for everything, and I had to compute V2 of S for everything. And now, all of that information, all I'm going to do is use this. So a lot of wasted computation has been done. It's better than total enumeration, because I did not enumerate all possibilities. But it's worse than some technique where I could have directly computed this. So what do you do here? It's again, take what can you spend on company 1, which is going to be the maximum of 0 on company 3 or plant 3 plus V2 of 5, or you spend, what is it? What was the project cost? $1 million? So it's going to be 4 plus V2 of 4. All right? So in the first term in that bracket, what I'm saying is that you don't spend anything on plant 3, and therefore you have all the $5 million for plant 1 and 2, and from that you end up getting this revenue, V2 of 5. If you spend $1 million on plant 3, then you get a revenue of 4 from there, and then you have only $4 million left over for plant 1 and 2. So if you look at these two, what do you end up getting? It's the maximum of 17 and 4 plus 14. So that turns out to be 18, which means that the best thing to do in plant 3 is to look at project 1 or project 2. Project 1 is nothing. Project 2 is to put $1 million. And now that you know that the best thing to do in plant 3 is to select 2, this implies that the best thing to do K2 star is going to be 2 or 3, which implies that the best thing to do at the first stage is what? Is to select project 2. Now let's just, the last step that I wrote over there, which I quickly wrote down, let's see if one of you can explain how I ended up getting that sequence over there. It could be. We'll see along the way. This is one of the errors that I do when I'm trying to online write down the solution to a problem which... so let's see, can we see, how do we justify this part? So this part is easy. This comes from saying that I chose this over that. So the best thing to do is not to spend 0, but to spend 1, which means that in K3 star, the optimum thing to do in plan 3 is to select this project. So K3 star is equal to 2. If you select K3 star equal to 2, this implies that the amount available for the plans 1 and 2 are going to be $4 million. So what is the best thing to do for plan 2 when you have $4 million available? You look at this answer. The best thing to do is select 2 or 3. So from here you end up getting that K2 star should be equal to 2 or 3. All right? And how do we get the last one? Let's go through the calculations of going through the previous one. How do I find out how much money that I have left over for the previous one? So what did we do here? We looked at what is the best thing to do at plan 3. I looked at the cost of that activity. Then I immediately know how much money I have available for plant 1 and 2. So the cost of activity 2 in plant 3 is equal to $1 million. From there I know that for plant 1 and 2 I have $4 million available. I look at this table corresponding to V2 of 4, and at that stage I know that it's optimum to use 2 or 3. So now what I have to do is I have to select one of these. Select, say, 2, I don't care. So if I select 2, how much money do I have available for plant 1? 2. And what is the optimum thing to do at 2? It's to select 3. And what if I had selected K2 of star equal to 3? What would have been the best thing to do here? How much money would I have left? Just let's go through the steps one by one. So if I had selected 3, how much money would I have left over? 1 million. And what is V1 of 1? 2. Okay. So there are two optimum solutions to this problem. K1 star, K2 star, K3 star. The optimum solutions are either 2, 3, and 1, or 2, 3, and 2, sorry, not 1. 2, 3, and 2, or 3, 2, and 2. So there are two optimum solutions for this problem, depending upon which selection you make. Questions about this calculation? So let's just review the steps of what happened here, and then we'll go forward and look at other examples. So the steps used are the following. And we have everything on the board, and I'll just go through slowly and show you what we did. We started out with this problem. We said that, well, this is a simple integer program. This is what we want to solve. Now, the first thing that we have to do is figure out some quantity that if I know that quantity, then I can start solving this problem in stages. The stages here is very clear. I have 3 different plants, so the natural thing to do is go plant by plant. First consider plant 1, then plant 1 and 2, then plant 1, 2, and 3. And if I had 5 different plants, then I would have gone stages by stages. Once I have decided what my stages are going to be, I have to figure out what is the information that I need to solve the problem at every stage. What is the only information that connects one stage to the next stage? In this particular problem, it's very clear that the only constraint that's connecting them is the budget constraint. If I can somehow decide what is the budget for each stage, I don't have to worry about anything else. I know the budget, I can solve that stage to optimality. I don't care about what happens to the other plants, I'm just concerned about the plants as long as I know the budget. So I decide, fine, the budget is going to be my state. What values can this state take? I look at the cost matrix and I say, okay, everything is an integer. So I need to solve this problem for states only taking integer values. Okay? Having done that, I go stage by stage now. In stage 1, I compute what is the best thing that I can do for just plant 1 for all possible states, 0 through 5. The next thing I want to do is do the same thing for plant 1 and 2. But in plant 1 and 2, what I notice is that part of the computation for plant 1 and 2 has already been done. So I take advantage of the fact that I've already computed the best thing to do for plant 1 by looking at a recursion. Once I got that recursion, I'm done. I can go as many stages I want. The only problem is that at every stage I have to compute this value for every possible value of the state. I have to pay this cost, but the computation is very simple. Okay, so I do that for state 2, and then I end up in stage 3 where I've computed what the best thing to do is. So far here I've only computed the best revenue. So all of this computation that we did, revenue in stage 1, revenue in stage 2, revenue in stage 3. We have computed the best possible revenue, which is 18. Now what I want to figure out is what is the best possible decision? What are the decisions that I'm going to do? And in order to get the decisions, I have to go backwards from here. So in order to compute the revenue, I came forward. I first came to stage 1, computed the best revenue, then stage 2, the best revenue, then the stage 3, the best revenue. In order to get the decisions, I'm going backwards. I'm going to start from stage 3, look at the best thing to do there. What is the best thing to do there? K3 star is equal to 2. Once I know that K3 star is equal to 2, I know its cost. Therefore, I know what is left over for stages 1 and 2 is 4. I've already computed what is the best value here. So the decision there is either K2 star is equal to 2, which tells me what is the money available in stage 1, which tells me what is the best thing to do here. There should not have been, there should be an implication here that K1 star is equal to 3, K1 star is equal to 2. So this story will repeat in every example. There will be some stages. I'll have to figure out some states which will decouple these stages. I'll have to solve this value function, that's why the letter V standing there, for every value of the state in every stage. Keep computing this forward. When I get to the final stage, I'll work backwards to get the optimum solution. Any question? Yeah.
Why this method is less tedious than the total enumeration? It's very easy to enumerate and see what's...
Yes. So the thing is, the question is, why is this method easier than total enumeration? You pay the cost of more stages and states and this cost of having a more complicated structure. But if you think about it, in order to answer your question concretely, let's figure out what is the amount of computation that I have to do here. Let's just compute the numbers. Let's say that every time I take an addition, it's unit cost. Let's just say that. So what is the total number of total computation I'm doing? And you'll see that there's a dramatic difference.
It's information plant 1 times information plant 2.
How much?
It's the product of the information of the number of projects.
Is it a product? Because if it's a product, then it's total enumeration.
Yes, but you have to choose the couple R1K plus R2L. So it's like...
No, but remember, I don't have to choose the couple here because I've already recursed it. If I were doing this, I would be doing total enumeration. So the basic difference between total enumeration and dynamic programming comes here. And that's why I kept this thing here to sort of keep the difference. If you do things this way, you're doing total enumeration. You're saying pairwise, saying what you have to do for stage 1, what you have, or plant 1 and plant 2. And if you computed things using this formulation, then you would do no better than total enumeration. And if you went to stage 3, you will have the three-way coupling. Here what we are saying is that half of this calculation has been done before. And let's leverage that. So let's look at what is the saving that you get from going from here to there. And we'll do it once and then, yes?
Didn't we get a condition like all the states mutually exclusive? It can't be the same?
Which one? I didn't.
I don't know, I thought in the...
So for every plant it's mutually exclusive, not across plants. So, and that we took care of it because we just said that from each plant we can take only one project. But that's another very interesting thing. If that had been there, then I was dead. Okay, so let's just do this computation and then we'll see. So if I want to, what is the total number of computations do I do in stage 1? What is the total number of computations that I have to do? The size of the budget, which is 5, times what is the computation I do there? It's some constant number. It's not a much more complicated than some. So it's proportional to, it's some constant times B in stage 1. What about in stage 2? So I have to do this computation for every value of the stage. And what is the computation that I have to do in order to compute the value for a particular value of the state? What kind of computation do I have to do? What is the worst case thing that I have to do? B. So the total computation here is of order B squared. Right? Every stage times, in every particular stage I have to compute 5 possible values from back there. So this, all I'm saying is that I have to compute V2S for all values of S. That gives me 1B. And in order to compute one value of V2S, I have to potentially do 5 additions based on what happens from the previous stage. So B squared is the total number. So in stage 3, I do the same thing. B squared. So the worst case computation grows as the number of stages, let's say n times B squared. Right? Now consider question.
B squared in stage 3.
What?
Stage 3, how is it again B squared?
It's the same thing, right? How is stage 3 different from stage 2? I mean, okay, you just computed once there, but if I had to keep on going for more stages, in stage 3 we computed only one value of V35, so we could have gotten away with just B, but I just wanted to have a general situation that if I had more and more stages, in every stage I'm going to do at most B squared computations. So if I have n stages, I'm doing n times B squared. Now if I were doing total enumeration, what will be the worst case in total enumeration?
Exponential.
It's B to the n. So that's the comparison that you have to do. In this particular case, it's possible that B to the n is actually less than n times B squared. So let's just do the computation here. This is 4 cubed is what? 64. And here it's 25 times 3, which is 75. So clearly, in this particular case, doing dynamic programming is a stupid idea. Just do total enumeration and you'll be happy. But the moment you start putting in just a few, the number of stages goes higher, dynamic programming really kills total enumeration.
You're going to look at average case instead of worst case.
You can't really look at average case because you have to compute the thing for every value of the state. Average case analysis here does not really make sense because in order to go forward to the next stage, you have to compute the value function for every state in the previous one, no matter what I'm going to do in the future.
But you won't have to do every one in the previous stage. You pick your, I'm saying in your average case, you won't have to go to the end, the last. You won't have to do the end calculation.
You will, because if you have got n stages in your problem, you have to go to the last one. It is true that different values, you will be going to different states in the last one. But no matter which state you go in the last one, you will have to do everything before. Even if you decide that the investments in the last 20% is 0, you have to still compute all the way till the end to decide that. So in some sense you are paying that cost, but it's something that you're going to, the only way you can get rid of it is by sampling, and there's this idea of Monte Carlo sampling that can be done, but it doesn't really save you much more. The other thing to remember here is that both total enumeration and the dynamic programming depend on the granularity of the number of states. If the number of states is large, both of these methods are going to die very quickly.
So,
Yeah.
can't we work backwards in this case?
Sure.
So you start with V3 of 5, and go back so that you know what all variables that you have to calculate. Like if we start with UFI, we know that we just have to calculate B2 of 5 and B2 of 4.
Sure,
So
you can do it.
This is the number of calculations that
In the worst case, it wouldn't. Because even in V24, in the worst case, it wouldn't. In this particular case, you can do whatever you want. In the worst case, you're getting off this order. I'm not saying that this is exact numbers. I'm just saying the only way you should keep this in mind is that here things go linearly with the number of stages. This particular thing, B squared, is it B squared or B, is not really that important, and it depends on the particular application. The crucial difference is that things happen here which go linearly with stages, and here it goes exponentially with stages. Question?
Is it we transform this entire problem into like some kind of network flow problem? Is it possible that we can find a more efficient way?
Sure, yes. If you convert this whole thing into a network flow problem, the question is that can we do it better? Yes, typically the problem, what happens is that, let me go back to the, I erased the cost matrix. So typically, if you can write this revenue as some linear function of the cost, then you can do it. But in this particular case, maybe this might work out, but here things are not very linear. So trying to do it by network flow would be hard. But indeed, if you could do it, that would probably be faster than doing dynamic programming.
What would the reason be?
Why would the reason? It's because in dynamic programming, in some sense, we are computing these corners which are, I know, useless in the next stage. I know a large number of these corners are going to be useless. So the way to think about it is that if you're trying to do LPs, it's like I'm solving a small LP, using the solution for that for the larger LP, but I'm only interested in the solution of the larger LP, so I don't have to resolve everything for the smaller LP. That's sort of the intuition. But if I can't do LP, then this is the best I can do. Okay? All right, so let's go with a couple more examples to just put down these ideas. So here's basically a summary of what we did. Your decision is divided into stages. Each stage has a number of states. A state is complete information needed to solve the problem at that particular stage. Given the state, the solution in subsequent stages doesn't matter. You don't really care about what happens later on. Yes?
Sure, just one other question. In every stage, I saw the computation complexity should be B instead of B squared.
Well, it depends on how you're counting. So the thing is this. In every stage, this component takes B different values.
Right, but the multiplier for B is that you actually don't calculate. You just look up the table.
Hold on a moment. But you have to do B different additions, possibly B different additions. So for every computation, you might have to do B different additions. It's not simply a lookup. It's a lookup plus something. So therefore, you pay a cost of B squared. But as the comment was being made before, if you worked backwards, that is, if you started from V3 of 5, then you know that you only want to compute these two. You don't really need to compute any more. So you can reduce your number of computations. But in the worst case, it will still be B squared for every stage. Okay. All right. Let's look at what's the next. This is an integer knapsack problem. Did Ali get around to doing 0-1 knapsack? Yes. So this is a generalization of that, where instead of having just 0-1 variables, we are going to have integer variables. So you're maximizing the sum over j going from 1 through n of vj xj, such that summation of j going from 1 through n of wj xj is less than equal to capital W, but now instead of xj taking values only 0 or 1, it belongs to the non-negative integers. 0, 1, 2, 3. You can take multiple copies of the same object. Okay? And we want to solve this using dynamic programming. Again, this is just like the case where with the plant, you can sort of think that we don't have these other constraint which says you can take only one project from the plants, but this is the linking constraint. This is the constraint that links the various xj's together. And if I want to decouple that, the state has to be the total weight. The total weight that is available for objects j less than equal to I. Question? So the stages in this case again would be defined by j taking values 1, or what did I do? I taking values 1, 2 up through n, and I'll decide objects j less than equal to I in stage I. And again we can work, let's go do it forward and then we'll work backwards. It will be pretty much the same. What is the state? If you assume that the vj's and wj's are integers, then the state here will be 0, 1, 2, all the way up through w. This is the weight available for objects j less than equal to I. Right? Okay. And I'm claiming that the right recursion, if I haven't done any typos here, is the one that's written there. Now let's try to make sense of what this recursion is doing. So Vj of W is the total revenue that I can generate using objects less than equal to j using a total weight of little w. And I'm claiming that that is equal to the maximum of these two quantities. Let's now try to make sense of what is this recursion saying. Can anyone volunteer to tell me what am I doing there? So just to keep ideas, what we were doing before was Vj of S was given to be the maximum of R, let's say Jk, where the project, kth project for plant J, plus V of J minus 1 of S minus Cjk, such that Cjk is less than equal to S. So the question is, what is this recursion doing? We'll have to correct that recursion a little bit. It doesn't quite make sense. I mean, there are two ways of correcting it, and we'll tell you.
Second term will be j minus.
Second term is not j minus 1. There is no typo there. That one is correct. And it has been put in red. So at least the ones that I put in red, I don't typically commit an error.
Should have put W instead of S.
Which one? Oh yeah. This should have been W minus Wj. True. But the J is correct. And this is what we want to figure out. What are we doing in that recursion? Okay, what is this? What does this part of the recursion mean? What is the value? What am I doing when I'm doing this? What am I doing? I'm not putting the jth object. So if I'm looking at the jth object, what can I do? I can either pick up the jth object or not pick it up, right? So if I don't pick up the jth object, what is the most revenue that I can generate? It's Vj minus 1 of W. The total bag weight that I have is W. I'd elected not to pick up the jth object. Therefore, the total bag weight of W was available for objects j minus 1 and smaller. And the best revenue that I could get out of there was this. What is this saying?
You're putting that object and then moving to the lower weight in the same.
But what does it mean? Why am I doing that?
Choosing the jth object and then you're doing optimization for a weight which is the weight less than the weight of the jth object.
No, I don't want to do optimization here. Once I have done...
V is the optimal,
Right, but this should be table lookup. I'm not doing any optimization. When I write a recursion, so that's one of the things that you should remember is when you're writing a recursion in dynamic programming, everything that falls on this side should be something that you already know. It's just an addition of a quantity. It cannot be something that you would compute again. So what is happening on this side? So two things are going wrong. First, the recursion Vj connects to itself. Do I run the risk of going in circles? No. Why not? You're always going in lesser weights. So I'm going to compute forwards, and therefore I won't run into circles. I won't go around, and I'm not self-referential. But what is this part of the recursion saying?
Integer value like 1, 2, 3, 4, same can be different number.
Right, but let's make it a little bit more clearer. It is 1, 2, 3, 4. This is 0. This is 1, 2, 3, 4. But why am I allowed to write this recursion?
The remaining capacity.
Somebody else said something. Okay, so just say in words what is this saying right now? This part. Yes?
We just want to take the object G
Yeah.
one time more.
We could possibly take it one time more.
And
So all this is saying is we take it once now, and if we take it once now, we immediately get a Vj, and all of you are pretty much getting to it. I just want to make it absolutely clear what is happening. Vj is the value that I get by taking this object right now. If I take that object, what's left over? It's W minus Wj. This is the weight that is left over. But unlike in the previous case, unlike in the plant case, unlike in the 0-1 knapsack case, I still have the choice of taking one more. And therefore, I cannot recurse back to j minus 1 here, but I recurse to j itself. At a lower weight, I want to ask again the question, do I take this object or do I not? If I take the object, I again still reserve the right to take one more. So the recursion here is going both backwards in stage and backwards in state. There are two different recursions are happening. One is in stages and the other is higher above in states, or states which are smaller. And therefore things are not going to go wrong here. Okay. Now how do we start this recursion? So far in dynamic programming, what you do is define stages, define states, and define a recursion. Make sense of the recursion in the sense that you have to convince yourself that when you write this recursion, in order to compute the left-hand side, everything on the right-hand side is already computed. You're simply going to take some additions and taking some maximization or minimization, as the case might be. All of these are maximization problems, but it could very well have been minimization problems. And this is true in this particular case because I'm going to start with V1, V2, V3, V4. So all of this is computed. And I'm going to, for a particular value of j, I'm going to start from smaller states and increase my state. And therefore, this is already computed when I'm trying to compute that. Now, how do we start this guy off? We need to get the value of one particular stage, and then we can start off. So what's the most logical thing if you look at that recursion, which is the state that you want?
We can consider the previous state as 0.
Which one?
V1, 0.
So there are different ways of doing it. Either you can keep track of which particular W's you want, starting from the front all the way to the back. Or if you don't really care about doing a bit of computations, and if I'm doing this in MATLAB, this whole thing is one command, and I don't really care about saving myself too much work for that, is to start from stage 1. If I know stage 1, I can keep on computing forward. And what is V1 of W? How would you compute that? In this particular case, it's going to be the maximum of 0 and V1 of W minus W1 plus V1. Right? And we'll use a convention which is that Vj of W is equal to, I have to put a convention of either plus infinity or minus infinity for W less than 0. So what will be the convention that I'm going to use here in order for this recursion to make sense? Minus infinity. I'm just going to assume, just so that the boundary conditions are taken care of, that V1 of W is equal to minus infinity for all W's negative. That way I don't have to worry about, so this recursion is not quite right because I have to make sure that Wj is less than equal to S or less than equal to W. If the total budget that's available for me is smaller than the weight of the object, I can't put it in. So just like in this particular recursion, I had this condition that I have to look at only those projects whose cost is less than equal to S. That particular condition is missing here, but the way to deal with that is simply to say that the negative value functions are minus infinity. Anytime it becomes negative, set it to minus infinity. In practical considerations, minus infinity doesn't make sense. So put some very large negative number and work with that. So that way you don't have to worry about trying to put boundary conditions. Okay?
You're taking max of a 0 and something else. You can't just put it as a negative any number.
Yeah, but this one is, yeah, but the thing is that you don't know what these v's are. I just simply said the v's are integers. If you, in addition, put that v's are non-negative integers, then indeed what you're saying is true. So in this particular case, since we didn't make that assumption, we have to allow for the possibility things can go negative. And you might be, so in one of the homework problems that's given today, you can either do it by traveling salesman problem or you can do it by dynamic programming. This is the currency arbitrage problem. There, your v's, the values, can be positive or negative, depending upon whether you get more money or less money. And therefore, things could be different here. Okay? All right. How much time do I have now? Okay. Let's go through one more example. This is a canonical example. In most courses of dynamic programming, we'll actually start from here, from this problem, the shortest path problem. And these two problems, dynamic programming or shortest path, they're basically the same problem. Every dynamic programming problem can be thought of as a shortest path problem in a graph. Or if you have, or as we have talked about dynamic programming, we can use dynamic programming to compute the shortest path in a graph. And this also brings up its own little complications. So here, for the first time, stages are not clear. It's not clear to me how do you define stages. So the problem that's given to me, it's the statement of the problem is that you've got n nodes. And let Cij be the length. And the length is in quotes because I'm allowing the possibility that Cij is negative of the arc Ij. So here's node I, here's node j. If I go from I to j, I pay a cost of Cij or get a revenue of Cij. So Cij could be positive or negative. I don't really care what it is. And what you've been given is a node S here somewhere and a node T there. Specified nodes. And what you want to find out is what is the shortest path that goes from S to T. So S is a specified node. And T is another specified node. And we want the shortest path from S to T.
So if Cij can take negative values, the more negative it is, you are more likely to take this.
Correct. Yes. So if it takes negative values, you would want to go along edges which have negative values. So for now, it's just saying that Cij's are some numbers. They're not necessarily integers. There are some real numbers, can take positive values, take negative values. And what we want to figure out is if I want to go from S to T, and I want to go in the cheapest possible way, how do I do it? So in this particular problem, it's annoying here. One of the things is that unlike the previous cases, unlike 01 knapsack, integer knapsack, capital budgeting problem, the stages are not clear. I'm writing down there at stage T as do something, but if I simply stated the problem up until here, it's not clear immediately how do you define the stages. And dynamic programming doesn't start off until you can define stages. So there are different ways of solving this problem, and the one way we are going to look at is to define stages by looking at the number of edges in a path. Okay, that's how I'm going to define my stage. I'm going to look for the shortest path going from S to T. Should probably not use the T both ways anyway. I'm going to go from S to T. In one case, I'm looking at the length of this path, and in the other case, I'm defining stages by just looking at the number of different edges here. And I'm going to say that V k of t, or vk of, what did I say? No. I'm using t over there, so you might as well use that. Vt of k is equal to the length of the shortest path. Again, the length is in quotes. And what is the, from s to t, or s to, in this particular case, so here's the particular situation that I'm looking at, using t or fewer edges. So maybe I should put a different name to this guy. Let's call this D, the destination. The source node and the destination node. So that's what I'm going to define. My stages are defined by looking at the lengths of the paths, and the state is simply the nodes in the graph. In every particular stage, I'm going to look at all possible nodes in the graph. And there are capital N nodes, and I'm arbitrarily labeling them k equal to 1 through n. The value of a particular node, a particular state, in stage t is given to be the length of the shortest path from s to k using t or fewer edges. So we're doing two things simultaneously. We're keeping track of the length, and this length is defined in terms of the costs. So if the cost of a particular edge is Cij, what is the convention that we would use for the length of the path? I'm talking about a length of the path. What is the convention that's most natural? Sum them up. So look at all the particular edges in the particular path and then add them up. So there are things that will go wrong. So let's concretize the ideas a little bit. A path from S to T or S to K, we would mean that no nodes are repeated. This is what I'll call the definition of a path. So for example, if you go from node 1 to node 2 to node 3 to node 4 to node 5, let's say, then back to 2 and then go to node 6, this I will not call a path from node 1 to node 6. Why? Because it has embedded in it a cycle. This particular path starts from 2 to 3 to 4 to 5 to 2. So this particular part can be sort of pinched out. This is a path. 1, 2, 6 is a path. But if you go to 2, go around a while, come back to 2 and then go to 6, I will not call that a path. So path has a definite meaning. It means a sequence of edges such that no node is repeated. And the length of the path is equal to the sum of the length of edges in the path. Okay, so those are certain technicalities about what is a path and how do we define the length of the path. So if I define my stages by looking at the number of edges in the path, and I look at the state where the state is simply all the nodes in that particular graph, then I claim that the recursion, the relevant recursion that I'm after is this. Vt of k, which is the length of the shortest path from S to k using t minus t or fewer edges, is equal to the minimum. And again, there will be some boundary conditions that we have to worry about. Cik plus v t minus 1 of I, such that I takes values 1, 2, up through n. Okay. Now let's try to make sense of that recursion. What's happening in that recursion? What's happening is the following. Here's my node S. Here's my node K. I'm looking for some path that goes here, and it uses t or fewer edges. Right? So this particular path that comes from S to K should have come from some other node previous to it. There must be some node on this path. In the shortest path, there must be some node I that comes right before node K. meaning that this is a right jump. It's a straight jump. It's not a path, it's an edge here. And what is the cost of that edge? Is CIK. Yes?
Cost is positive from I to k and negative from k to I.
Nope. They're two different numbers. Nobody said that one is positive, one is negative. CIK has got nothing to do with CKI. They're two different numbers. The cost of going from I to k has got nothing to do with the cost of going from k to I. One way you pay toll, the other way you don't pay toll. So there is no relationship. Okay? So far all I'm saying is that let's say this wiggly path that has been written now is the optimum path that goes from S to T or S to K using T or fewer edges. And then let's say that this particular path goes through I. And what can you say about the length of the path from S to I? How many edges is it using? T minus 1 or fewer. Okay. So this particular piece uses T minus 1, less than equal to T minus 1 edges. And what will be the cost of that path?
At least as much.
At least as much? What is the best thing that you can do? So for now, let's forget about what happened later on here. Okay. Now suppose I want to get to I using some old path. I don't care what path it is, but in the cheapest fashion. But using T minus 1 and fewer edges. What is the length of that path? By definition, this is this. Could this have not been the optimum path? No. Why not? Exactly. If this piece of the path was not the optimum way to get to I would have taken this piece out and replaced it by the shortest path going from S to I. Right? And therefore, if indeed the shortest path coming into K went through the node I don't know whether this is going to happen, but suppose the shortest path coming into K went through the node I, and I jumped from node I to node K, then the length of that path would have been exactly this. CIK is the last bit. VT minus 1I is the cost of going from S to I using T minus 1 or fewer edges. Right? But I don't know which node I'm going to jump in through K, and therefore I take the minimum over all possible nodes. And I allow the possibility of jumping from K to K, meaning that if you allow T edges, you do no better than using T minus 1 edges. And in order to allow that possibility, I'm just going to say that CII is equal to 0 for every I. Yes? Exactly. And that is why I went through this whole mess of trying to define what the path is. So, good question. The question is that, and that's why there is a question right above, below this, which is, will this recursion always work? Now, the definition of a path says that I cannot allow node K to appear anywhere here. If the node K appears anywhere here, that's not a path, because it has a cycle in there. Now, if you apply that definition to here, to node I, then all it's saying that in the optimum path coming into I cannot appear. But it doesn't say anything about K. So K could have appeared here. Somewhere here was K. You came through K to I and then jumped to K. Right? It's possible that this would happen. And if that happens, then you're not getting the path. And therefore, this recursion, although it pretends as if you are computing paths, is not computing paths.
Are you not going to forbid cycles?
I'm forbidding cycles. But here it doesn't forbid cycles. This recursion doesn't care about cycles. It simply is saying, look at this node I. When it's looking, what is this recursion doing? This is one of the sort of the power of dynamic programming as well as the cost. What we are trying to do is we want to keep as little information around. So when we look at the optimum path coming into I do not care how I got into it. For now, I don't really care. All I care is what is the shortest path.
You keep a linked list, right?
The linked list simply tells me that means I have to go all the way back every time to keep checking. That's like total enumeration. Yeah?
So how can upcut and K in this path?
Good question. How can it happen?
Because there's a minimum.
If you have negative.
What? There's a minimum. But there is a particular situation in which this can happen. And in that situation, this recursion fails. When on a loop, the cost is negative. And therefore, you keep on looping until you sort of drive that cost to minus infinity. That's the one situation in which this can happen. And since I'm allowing Cij to be negative, I have to worry about this situation. I have to worry about the situation that there is a negative cost cycle. There's a cycle such that if you add up all the costs along that cycle, you get a negative number. If you get a negative number, it's beneficial for you to keep circling. And something like this can happen. Okay. So this recursion will work as long as there are no negative cycles. As long as there are no negative cycles. It could have negative costs. But as long as there are no negative cycles, we are okay. Because then I know that it will never cycle. And therefore I know that this node could not have appeared anywhere before. And I can recurse through this to compute the best thing. Okay. Now how would I detect it? So I'm merely going around trying to compute this recursion, right? I can't look at the entire graph. I don't want to go there trying to search for negative cycles all the way. So I want to somehow just do this recursion because this is a cheap recursion. And somewhere at some stage say, okay, this has negative cycle, and I give up at that point. If it has negative cycles, I can't do dynamic programming because I have to keep track of how the path came. And the moment I keep track of this entire information, I'm doing enumeration. So dynamic programming will not work, but at least I want to figure out whether I'm going to get the right answer or not.
You can set a lower bound, anywhere for one negative value.
So you can try to look at the negative arcs and then try to take those off.
No, I can't take them off. I can't take negative offs because if there is no negative cycle, those negative arcs are very good. They're reducing my cost.
But if you take the negative arc off and then you try to find the path and if it doesn't find it, then that is the...
But then that's total enumeration almost, right?
Find the lower bound by looking at the negative arcs.
And then do what with it?
And if our value is going below that,
Yeah.
we know we are looping in our negative.
Yes, that's a good solution. But now the question is that I have to solve this problem twice. Right? So the suggestion that's given is remove all the negative arcs and then look at what happens. Typically, the users of these technique will complain about it in two ways. One, when you look at shortest path algorithms, typically you want to keep only local information. You don't want to keep the entire graph in your memory. And what you're suggesting is I have to search the entire graph to figure out where those negative arcs are, remove them, do another calculation. But there is a cheaper way of doing it.
So what I'm saying is you actually look at all the negative arcs in the total graph,
Right.
and set a lower bound on the total cost.
Right?
And then if the value drops below that,
Right.
you know we are recurring.
Yes, but that's only, that's not necessary, right? It's sufficient. If it goes down, then I know there is a negative cycle. If it doesn't go down, there can still be a negative cycle, right? So there's a little discrepancy there. But I thought what you were saying was to remove the arcs and then do a computation with two paths. That would detect something, but it's not local.
Can we just check at each recursion?
What do we check?
If the heuristic function is positive.
Yeah, but the problem is that this fellow, this length guy, is actually negative. It can have negative edges. So it is possible that the length to a particular node is negative. But what we are trying to figure out is that is it a legitimate negative number, or is it a negative number that we have gotten by going through cycles? So let's look at one more thing before let's go up, try to compute this answer by looking at one more fact that I haven't stressed so far. And I'll just talk about that and then we'll leave. What is the largest value of t that I need to consider? What are the number of stages that I need to consider in this particular graph? N or n minus 1? N minus 1. If total number of nodes in the graph is n, then the number of stages, so t has to be less than or equal to n minus 1. The number of edges in a particular path has to be less than or equal to n minus 1. Now let's do the following. We compute Vn minus 1, k, and then we do one more step. Vnk, let's say. We just waste one more step. Now if there were no negative cycles in this graph, do you expect Vn minus 1k to be different from Vnk? Meaning, is Vnk going to be better than Vn minus 1k?
No.
No. But if there were negative, what will happen?
Yeah, it will be better.
You will complete a cycle and at least one of the numbers will go down. So that's the way to check, which is a cheap checking strategy. You go up to n, instead of stopping at n minus 1, go up to n. And if in the last stage the value for any of the node drops, it means there is a negative cycle, which means that you cannot trust any number here. It's not just that node that you cannot trust any node. But if it doesn't happen, then at this stage, the answers that you get here or here are the exact solution. Okay? All right, let's break here. In the afternoon, we'll do a numerical example to see how this works out.